Let's talk about exponential functions. And an exponential function f with the equation f of x equals a times b to the x. If you increase x by 1, it causes the function value to be multiplied by a constant amount b, the growth factor. Sometimes this value is described as a percent of change. So for our equation, f of x equals ab to the x, a is our initial value, and b is our growth factor. So in contrast to exponential functions, linear functions are in the form y equals mx plus b, where b is added. Whereas the b in this equation, b is what it's multiplied by each time. So the town of Centerburg is suffering from a decline in population. Nobody wants to live there. I don't know why. Maybe it gets to be -20 in the winter, like it is here. Although I love it here, but it's way too cold. So a demographer has predicted that under current conditions, the population will decrease by 2% each year over the next decade. But then a manufacturer says, hey, we're going to bring in a factory that makes shoes. I don't know, maybe it's shoes. It makes shoes. And that'll reverse the trend. The population will grow by 4% annually instead. So we'll make two equations. So function f, where the population of 28,500 increases by 4% each year, and function g, where it decreases by 2% each year. As far as a percent goes, so if you multiply by 1, nothing changes, right? So that's essentially multiplying by 100%, so adding 0%. If you want to increase 4%, we're essentially doing 100% plus 4, which is 104%. But in terms of, in an equation, we do 1 for 100% plus 0.04, which is 1.04. So then f of x equals, well, we're starting with 28,500, and we're multiplying by our growth factor of 1.04 to the power of x, where x is the amount of years. For g, we're decreasing, so we're decreasing by 2%, so that's like 100 minus 2, which is 98%. But in terms of in an equation, if you multiply something by 100, that's much bigger, right? Multiply by 1, that's 100%. Let's subtract our 0.02, and we get 0.98. So what we end up using is our 1 plus 0.04 and our 1 minus 0.02. So then our g of x, we're still starting with our initial population of 28,500, but now we're going to multiply by 0.98 to the x. So now if we compare the projected populations after 10 years, well, f of 10, so let's see, the factory, the manufacturer claims that it'll grow, so f of 10 is 28,500 times 1.04 to the power of 10, and in most calculators this is 28,500 times 1.04 caret 10. Either way, that predicts the population will be 42,187 people in 10 years. The demographer, who thinks the population will shrink by 2% each year, g of 10, so he thinks, or she, I guess, I don't know, 28,500 times 0.98 to the 10th, or 28,500 times 0.98 caret 10, equals 23,000, just froze on me, oh, okay, 287. So when an exponential function has a growth factor greater than, switch colors, greater than 1, it is called an exponential growth factor, because if you multiply by a number greater than 1, your number will grow. a function whose growth factor is between 0 and 1 is called exponential decay, because if you multiply by a decimal, essentially less than 1, your number will shrink. So one common exponential function, other than what we've talked about, is a equals p times 1 plus r to the t. And this is the equation for compound interest. Where p equals your initial amount, r equals your rate as a percent, and t equals your time in years. So if we look at our example, if a equals p times 1 plus r to the t represents your balance after t years when you're investing p dollars. Suppose $2,500 is invested with a 5.3% annual yield. So the equation for your balance after t years, so your general equation, we're starting here, but we have a equals, well, we have our p, it's 2,500 because we're told, times, well, 1 plus, we know our rate, 5.3 to make it a decimal, 5.3%. You divide it by 100 or move the decimal 2 to the left and fill in a 0. So we get 0.053 to the power of t. That's the general formula. And after 7 years, we can plug 7 in for t. 2,500 times 1 plus 0.053 to the t, but it's not t, it's actually 7 now, because we know it's 7 years. And this ends up being $3,588.71. Examples 1 and 2 that we just did, so we're looking right here, illustrate that the value of a in f of x represents the initial value, which I kind of already told you. Sorry to spoil the fun. And a and b, a is the initial value, b determines whether it's exponential growth or exponential decay. Now we look at graphs. So pause the video for a moment and do this matching activity. Okay, I'm assuming you tried and you came back, or just want to listen to me because you do. So if we look at this here, so our initial value is really our y-intercept. So A is really our y-intercept because it's our initial value. So if we look at A here, this should have an initial value of 5 because that's our y-intercept, and it's an exponential growth function. So I'm looking for a 5. The only 5 I see in the A spot is number 6 here, okay? So 6 goes with A. And again, the reason why I can tell this is exponential growth is because 2 is bigger than 1. If we look at B, our initial value is 8. So we're looking for an A of 8, and then it's decay. So let's see. So here's a slight problem, right? Because I see 2 8s with decay. However, we have another point. We have the point 1, 2. So let's plug it into those equations and see which one works. So 8 times 0.5 to the first power is 8 times 0.5, which is 4. So that's not the right equation. Let's try the one above it. 8 times 0.25 to the first power is 8 times 0.25, which is 2. So that fits. So number 2 is B. If we look at C, our initial value is 1, and it's increasing. Another one that works for that is number 4, because if you look, technically this is the same as 1 times 3 to the x. So our initial value is 1, and we're growing. just going to get rid of these extra scribbles that I just kind of increased, but number 2 was B. Okay, let's look at D. So this one we're really going to have to use points. We know it's decaying, we're going to have to use points. We have the point 3, 1, and we have the point 4, 0.5. So, first of all, we know it's not an initial value of -20, so it's not that one. Thank goodness, because we don't have to plug these numbers in. Let's see, is it decaying or growing? I mean, all we have left, except for the initial value of -20, which can't be this one, all we have left is 6 times 3 to the x and 8 times 0.5 to the x, and the only one that's decaying, like this function is decaying, is 8 times 0.5 to the x, so that must go with D. If we look at E, this one, the initial value looks like the initial value is somewhere between 2 and 18, somewhere right there. So it's definitely not -20. So it looks like this one's got to be number 1. And then number 5, conveniently, the initial value is -20, and it's growing. So this is F. Keep in mind there's a ton of other ways you could have figured this out. If you're like, I didn't think of it that way, that's totally fine. And in each of these graphs, the x-axis is a horizontal asymptote of the function. So now if we compare and contrast here, if we look at our linear function over here, the domain, left to right, x can be anything, so the domain is -infinity to infinity. The range, bottom to top, y can be anything, so -infinity to infinity. Y-intercept looks like it's 8. X-intercept is -4. Asymptotes, none. Lines don't have asymptotes. For the exponential, the domain, it looks like x can technically be anything. It's kind of different because it looks like it's maybe an asymptote here, but really it's just going to the right like really slow, but it's eventually going to make it. So our domain is -infinity to infinity. Our range, we have an asymptote at 0. So our range, bottom to top, doesn't start until 0. And it's not included because it's an asymptote and goes up to infinity. Our y-intercept, it looks like I kind of scribbled all over it. But if I look back at what we had, it looks like it was maybe 8. Our x-intercept, none, because there's an asymptote. And our asymptote is this horizontal line, so it cuts through the y-axis. So it's y equals 0.